All right, let's go ahead and get started. We're doing chapter number 7 today. But before we do that, I'd like to talk just a little bit about the flame tests that we did last week and why it works and how it works. Typically, a flame test is done using a bit of wire. This works best if this is platinum wire. They don't use platinum anymore because people kept breaking it off and stealing it. You get a gram of it, it's worth $30 or so, I don't know. But, so they use nichrome. And nichrome really doesn't work very well. You get lots of contamination. So we use the sprayers. But okay, what happens when you take your metal ion and put it in a flame? Well, the electrons absorb energy, is what happens. When they absorb energy, they can jump from whatever quantum level they're at up to a higher quantum level. Now, remember, quantum levels are like steps, so they're uniform in energy. Once these little guys get up here in outer space, they look around and say, why am I here? And they want to go home. But they have to shed this energy that they absorbed. They do that by emitting a photon. Because this is quantized, this is only one wavelength. Different energy level, different wavelength. That means that the element emits light. The light will occur at very distinct wavelengths, and that's called the emission spectrum. The emission spectrum is unique for every atom because the electron configuration is unique for every atom. This is how you can look at a star that's 100 million light years away and know exactly which elements are in that star. It's kind of an interesting technique. You can break down the light from a flame test using what's called a spectroscope. And a spectroscope is kind of difficult to use because you have to look this way while you're pointing it this way. But if you do that, you can see the lines on a little scale down here. For a fluorescent light in the room, you would see something like this. Now, as we look at fluorescent lights, they're white, right? That's because your eye averages all of these into a single color. Same thing with a flame test. We're actually getting lots of distinct lines out of this, but your eye averages them into one color. And that's why every element will have a unique color. Now, like I said, we didn't use the wires because they don't work very well. We used spray bottles. They work better. But probably the most fun way to do it is this way. What you do is you have your little lecture desk, you line up watch glasses, put solutions in each of them, turn off all the lights, and do this. Set it all on fire. So you just...
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with barium ions burning a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
So this is a really fun way to do it. But again, they won't let me do that here anyway. This is how fireworks work. This was supposed to be the Olympic fireworks for 2020 that never happened. Well, Japan had all these things that were going to go bad, so they just shot them off anyway. But all the distinct colors are metal ions. So that's how you make fireworks. Isn't that neat? All right. We're talking about aqueous solutions. This is water. In this chapter, we're going to start off talking about dipoles, electronegativity. We're going to talk about how things dissolve in water, the concept of solubility, electrolytes, non-electrolytes, molarity, very important concept, and dilution of solutions. Any questions before we get started? Well, we've talked about bonding. We said we had two types. We have covalent and we have ionic. In covalent, we said atoms share electrons. In ionic, one atom donates an electron to another. Okay. In reality, these represent limits. Bonding in reality is somewhere between these two typically. Let's look at how we make a covalent bond here. Again, to make a chlorine-chlorine covalent bond, you would simply bring in another chlorine atom such that each chlorine has 8 valence electrons. We expect the sharing here to be perfect, and typically if both atoms are the same, it will be darn near perfect. They share nicely. But if you have different atoms in your covalent bond, which you typically do, then things are not quite the same. Let's look at 2 examples here. This is hydrogen, H2, the element, and this is hydrogen fluoride. They're both covalently bonded. What we're going to do is use what's called an electrostatic potential map to examine the charge distribution along a covalent bond. What you do in electrostatic potential map is it's a thing you do on your computer. You tell your computer to look at your atom, your molecule, and decide how or where the electrons are in this covalent bond. So it does this calculation, starts in the middle, goes out, and stops when it hits region that's about 90% probability that that's where the electrons are. Then you take a point in your computer on your surface and you measure the electron density. And you do that over the entire surface. So now you know electron density. Then you take and you use a color code to display that. So for hydrogen, the distribution is quite uniform and it looks something like this. All right, they're both the same. That's good. You expect them to share nicely. Hydrogen fluoride is somewhat different. We're going to do the same operation. Start here. We're going to look to see where the electron density is. Right away you can tell something is different because the electrons are mostly down here by the fluorine, leaving the hydrogen without any. If we color this, we see a beautiful little Easter egg. In the color scheme, Blue represents electron deficiency or a positive charge. Red indicates excess electrons or a negative charge. This is an example of a polar covalent bond. Hydrogen, they were the same, it was uniform. HF, very, very skewed with the electrons mostly by the fluorine. We can show this charge distribution using what's known as a dipole. It's really just an arrow with a positive sign on one end. And this shows that this covalent bond here is polarized. Positive on this end, negative on this end. Now, why does this happen? Well, it's the concept of electronegativity. Electronegativity is the ability of an atom, an element, to attract electrons towards itself. There's a scale that goes from supposedly 0, although 0.7 is the lowest we have, up to 4. This corner is the highest electronegativity. This corner is the lowest. Hydrogen is over here, has electronegativity of 2.2. Fluorine was here at about 4. That's why the bond is polarized. The electrons are attracted to the very electronegative fluorine. Okay, well, this is a chapter where we talk about aqueous solutions, right? So what does this have to do with that? Well, here's fluorine, and right next door is oxygen. What is water made of? 2 hydrogens and an oxygen. So let's see the effect electronegativity has here. Let's start off with the Lewis structure for water. Water is here, or oxygen is here in group 6, so 6 valence electrons. Hydrogen group 1, we have 2 unpaired electrons. We'll simply stick them in like this. Now, this is the representation for water. It's a Lewis structure. You could draw it any way you want. But I've drawn it specifically with these guys at right angles, because that more or less describes how water really looks. The geometry of the water molecule. The geometry is what we call bent. This is what water looks like in a model. We have 2 unshared pairs of electrons and 2 bonding pairs of electrons. The reason that this is bent is something called the valence shell electron pair repulsion theory, VSEPR. Basically, what this theory says is that these electrons, all of them, electrons in bonds and unshared pairs, are going to repel each other. And they're going to arrange themselves in space in a geometry that minimizes their interaction. So they get as far away from each other as they can. This is a little movie showing us. If we had our central atom here, we had a pair of electrons here, a pair of electrons here. The way that they can get as far apart from each other as they can is by making a linear bond, 180-degree angle. If we bring in a third pair, we get 120-degree angles and it's flat. The fourth pair gives us what's called tetrahedral geometry, and that's what water is. It's tetrahedral. These angles are 109.5 degrees. Okay, well, so water is bent. We looked at the table of electronegativities. We said hydrogen was about 2.2 and oxygen was 3.4. Our prediction here is that these covalent bonds will be polar. The oxygen will draw the electrons away from the hydrogen, and we have two little dipoles like this. Now this is a molecule. The prediction now is that since the positive charges are here both on the same side, and the molecule is bent, that this end of the molecule will be positive, and this end will be negative. That is, we expect a molecular dipole from here going up through the molecule towards the oxygen, looking something like that. Now, we can check this out by calculating the electrostatic potential map for water. When we do that, it looks like this. And by George, big blue bottom, red top, here's our dipole. So the simple conclusion here is that water is a very polar substance, very polar molecule. This is the thing that makes water so special. This is the reason that life can exist, to be very basic about it. It's also the reason that water can dissolve ionic compounds, such as sodium chloride. It dissolves them, makes a homogeneous mixture or a solution. Here's a little movie that shows this in action. This represents a crystal of solid sodium chloride. When I click the little button here, animated water molecules are going to come in, and they're going to pick ions off of the surface and carry them away, one by one. So let's watch. Here they come, they grab a sodium, and they grab a chlorine, another chloride, another sodium, etc., etc., and this just goes on until your crystal dissolves. Now, I hope you were paying attention as these little water molecules were doing their thing, because the way they grabbed the ions off the surface was not random, not at all. If you note, here's our cation, here's our water surrounding it. Looks something like this. There's the sodium ion, here's the waters, and you'll note that all of the oxygens are pointed towards the sodium. Over here we have the chloride. All of the hydrogens were pointed towards the chloride. That's because this is the positive end, and this is negative. So we wrap this guy up in these little positive bottoms of our water molecule. Same thing over here. This is the negative end, and what this does is it disperses the charge. Now, nature really abhors a single point charge, really doesn't like a charged thing at all. This allows that charge to be dispersed over the adjacent water molecules. We can show that actually using yet another electrostatic potential map. Here, this represents the sodium cation. It's blue because it's very positive. I have put 3 waters around it. I tell my computer to calculate an electrostatic potential map for the entire complex. What you see when you do that looks like this. Our big blue ball that was here in the middle is gone. All you see remaining are little blue tips out here. In fact, the central blue ball actually looks a bit yellowish. Water is just phenomenal at grabbing and dispersing charge. Not only that, but water doesn't really just live in groups of three. In fact, it lives in clumps of about 12. Very dynamic clumps, but about 12 waters per ion. We will see in Chapter 8 that the effect of the 12 waters is phenomenal. So much better than this even. But that's Chapter 8. Any questions? So bottom line, water can dissolve ionic species because it can disperse the charge and make it much more stable. Let's talk a little bit about the concept of solubility, definitions, and whatever. Solvent is the thing doing the dissolving. Solute is what we call the thing being dissolved. When we say something has a solubility, that's represented by a number, usually in grams per liter. Magnesium carbonate, for example, at roughly 298, that's room temperature Kelvin. We don't know that, but 25 degrees. The solubility is 0.53 grams per liter. So we can take magnesium carbonate at room temperature and dissolve about half a gram in a liter of water. Now, there's one cute, fun fact about all this, and that is you could sometimes cheat. With certain compounds, if you're very, very careful, you can warm them up and dissolve more than their solubility allows, because things are more soluble in hot water. Then you let them cool, and you wind up with a solution that's not just saturated, but it's called supersaturated. Basically, you have too much of the stuff in there. Think about fries. This is fries. That's supersized, too much, right? I have a really neat little video here of a supersaturated solution that we're going to drop a crystal of sodium acetate in, and it's going to unsaturate, go back down to being fully saturated. So, in this flask is sodium acetate. Quite a lot of it will dissolve when the water is warm. If you very, very, very carefully cool it, and nobody walks hard, nobody touches it, nobody breathes on it, the solution is stable. Cools down and is stable. It's supersaturated. What we're going to do is take a single crystal of sodium acetate, drop it down the neck of this thing, it'll land about there. Let's watch. About there. There it goes. Instantly, this stuff starts to crystallize out. There's enough in here that this essentially sets solid. The solution actually gets very hot at the same time because you had to put heat in to get this to dissolve. So it gives it all up as it comes out. So the liquid that's left in here is saturated, no longer supersaturated. Kind of a neat little thing to do. Any questions? Solubility, there's a rule of thumb. Like dissolves like, where like refers to whether you are polar a polar molecule, polar compound, an ion, or non-polar. Alcohol has an OH just like water. That makes the molecule polar. We can add as much alcohol as we want to water. It will dissolve. It's called miscible, miscible in all proportions. If you have a nonpolar molecule, because water is a polar solvent, it doesn't mix at all. It just forms little globs. This is oil being suspended in water. Again, it does not dissolve because oil is nonpolar, very insoluble in water. Alcohol, very polar, very soluble. Any questions? Well, when things dissolve in water, the solution that they form can either conduct electricity or not. This is called electrolytes and non-electrolytes. An electrolyte, the solution will conduct electricity. Non-electrolyte, it will conduct electricity very poorly. We'll understand why in Chapter 8. But okay. Again, electrolytes conduct a current, non-electrolytes do not. Very simple concept. There's a way you can test for this in lab. This is a device that we used when I took general chemistry a long time ago. Basically, you have plates, metal plates that you immerse in your solution. These are connected to a light bulb. And you power this up. Now, how did we used to power it up in the old days? Very simply, you plugged it in the wall. Now think about it. You have a class of 50 freshmen. You have open metal plates at 120 volts. And you have a solution of water that probably will conduct electricity. It was disaster just waiting to happen. Nonetheless, we did it this way. This represents a non-electrolyte. No ions, nothing is happening, does not conduct electricity. If you have an electrolyte, the ions are very mobile in solution. They facilitate the current going from the anode to the cathode. When this does, it completes the circuit, and your light bulb would glow. There's a third type, not just non-electrolyte or strong, there's what's called a weak electrolyte. A weak electrolyte, something like acetate. This is acetic acid. It's the acidic component of vinegar, and it ionizes in water. It's a very polar molecule, so it dissolves in water. But when it ionizes, well, when a strong electrolyte ionizes, you get virtually 100% ions. When acetic acid ionizes, the ratio is about 100,000 to 1. So we get very few ions in solution. Because of that, our light bulb barely glows, called a weak electrolyte. So non-electrolyte, strong electrolyte, and weak. Today, we don't use light bulbs plugged into the wall anymore. Thank goodness. Today we have a much nicer set of tools. Something like this. It's a little magic wand that you can put in your solution, get a numeric value. Microsiemens per centimeter is the unit, but the number is what you want. So you put it in a strong electrolyte, you get a big number. Put it in a weak electrolyte, you get a much smaller number. And you put it in a non-electrolyte, in water, you don't get 0. You still get a number. That's because water by itself, and this is chapter 8, water by itself auto-ionizes. Autoprotolysis it's called. There are always ions in water. That's why you can't take the hairdryer in the tub. Right? Right. The bottom line with electrolytes and non is ions. If your species forms ions, it's an electrolyte. Here we go. These hydrated ions facilitate the flow of electricity and you get a big number. If you have a weak electrolyte, you get very few ions being formed. Sugar, very polar molecule, dissolves nicely in water, doesn't it? But it does not ionize, so it's a non-electrolyte. Any questions?
Is this similar to like how the battery goes? Or no?
Is that, well, these are battery operated.
No.
Is that how a battery works?
Yeah, like
No,
the
a battery
charge.
works by redox reactions. Remember, in a redox reaction, we transfer electrons. So in a battery, you have cells that each undergo redox reaction. The electrons flow out of one and back into the other.
Was that what the light was doing when you had it, when the pitcher had the two
Yeah.
things in the solution? That's basically what it was doing, right?
Yep. Yep, except it was 20 volts, and you touched that, you were fried. It was very, very unsafe. Nonetheless, that's what we used. They didn't care in those days. All right, well, this was a very nice break after chapter 6, right? Very descriptive, pretty pictures, no calculations. Well, that's about to end. Because we're going to talk about the concept of molarity. Molarity, quite simple, is the number of moles in a solution over the volume of that solution in liters. Moles divided by volume in liters is molarity. Quite simply, this is a volumetric flask. Volumetric flask is an expensive piece of glassware because it has a little line etched in the skinny neck here. Kind of like the volumetric pipette we used in lab. Little tiny skinny line. When you fill the flask exactly up to that line, that contains 1.00 liters. You can get them in all sizes. So this is 1 liter, right? This is 1 mole. We have 1 mole per liter. I apologize for that. This would be a molarity of 1. 1 mole per liter. In reality, we know that chemical reactions take place in aqueous solution. We know that because in lab number 6, you did a whole bunch. And you got precipitates or whatever. In order to be able to calculate the parameters, you need to know exactly how much stuff is in there. The way you do that is by knowing the molarity, the number of moles per liter of solution. Now, the abbreviation for molarity is an uppercase M. There are many variations on it, but it's always uppercase. In general chemistry, you will meet something called molality, which is darn near the same as molarity, but different. That's in lowercase m. So make sure you're always looking at uppercase m's, some variation for molarity. Now the way you make a solution of known molarity, we're going to take a solute of some sort. We're going to carefully go into lab, and we're going to weigh it out. So we know exactly what mass we have. We know what the stuff is. You know its molar mass. You know the number of moles you're dealing with. So you take that and transfer it to your empty flask. So there it is. Then you very carefully add water in the flask until it comes up to exactly the little X line at 1 liter. You know the volume in liters. You know the number of moles because you weighed it out. Therefore, you know the molarity. It's a simple concept. Any questions? Then let's do a problem. We have a solution. We weighed out 3.2 grams of sodium bromide. We have 1,250 mils of total solution. What's the molarity? Well, we know in order to calculate molarity, we need to know the number of moles of sodium bromide we have. Divide that by the number of liters. Now our volume was given in milliliters. So we just can do this in our head now. Divide that by 1,000, that's 1.25 liters, right? How do we get grams into moles? Well, we remember mass divided by the molar mass gives us moles, doesn't it? Told you to remember that one. So, this gives us the total number of moles. Divide that by 1,000. This is the number of liters. Moles divided by liters will give us molarity. Now grams cancel, that's no problem. This is 1 over mole. Okay, mole minus 1, 1 over mole. And it's in the denominator up here. We have basically 1 over 1 over. The reciprocal of a reciprocal is what you start with. Turn something over twice, you're back where you started. So that's just equal to mole. So this mole comes up top, and that's our units. Mole per liter. Do the simple math. 0.0253 moles per liter. That's 0.0253 molar. Now, depending on where you're looking, the uppercase M can be in a variety of forms. Some people just use it as N and M. This is just an italic. Sometimes it's underlined, sometimes it's italic underlined, and sometimes it's script. But remember, it's always uppercase. Any questions? That's simple, isn't it? Let's do it again. We have 6.47 grams of sodium acetate. There's its molar mass, and we have 1,450 mils of solution. Again, moles of sodium acetate divided by liters. Moles of sodium acetate, we have a mass and we have a molar mass. That's moles. Divide this by our 1,450 mils converted to liters, 1.45 liters. Grams will cancel. per mole will come up top, and we're left with 0.0544 moles per liter. On an exam or so, you would see it written out this way with liter minus 1, because that's easier to do. Or just use the uppercase M. Now, there are a number of varieties of ways that you can ask questions about molarity. This is just like the one we just did. Why don't you go ahead and do this one? 238 grams, 174 grams per mole, and we have 275 milliliters. You want to figure out the number of moles and divide it by the number of liters. So just set this up quickly. To get the number of moles, we want to take our mass, divide it by our molar mass. Divide this by 1,000 to get 0.275 liters. Grams cancel, per mole comes up top. We do the simple math. 0.4969 moles. We have three significant figures. Therefore, we round to three figures. All right, there are two tutorials dealing with molarity. I call them lovingly Molarity 1 and Molarity 2. Molarity 1, everybody loves it. It's a table. Everyone loves working on a table. When you hit new problems, something comes up missing. Here, molarity is missing. We know that molarity is simply moles divided by volume. So, moles divided by volume, 0.976 divided by 2.15 liters, and we're at 0.454 molar. Every time you click new problem, something comes up missing, like I said. This time, volume is missing. You only need one formula to remember or write down on your card. Moles divided by volume. So volume would be moles divided by molarity. Moles divided by molarity gives us volume. Substitute the numbers. We're in 4.26 liters. And finally, if moles are missing, moles are going to be molarity multiplied by volume. Molarity multiplied by volume gives moles. 0.125 times 2.92, 0.365. Now, here's something that we just did that's worth remembering. Remember I said mass over molar mass was good? Well, what we did here was to take concentration, that's molarity, multiplied it by volume, and we got moles. So remember this one. Concentration times volume is moles. Worth remembering. All right, so let's look at some more problems. This is a variant on our standard, and it's kind of like real life in lab. You have a stock solution of something. So they make up a concentrated solution. You are running an experiment. You calculate you need 0.01 moles of KCl. So you're going to take and measure out a certain volume that has 0.01 moles in it. Question is, how do we do that? Molarity is moles divided by volume, right? We're looking for a volume. We simply need to divide moles by molarity. So, our moles, 0.01, our molarity, 0.18, moles and moles per liter cancel, liter comes up top, and our volume of our solution, 0.056 liters. Now remember, whenever you do this, you're going to get an answer in liters. In lab, you would measure this out in milliliters, 56 mils. Yeah.
In high school, they taught us to put like a dash on top of the 5 because it's 0.055555.
Oh, it is?
Yeah. Instead of that, I'm not sure if that's.
Well, we're only dealing with two significant figures, so that's good.
So if we were to put on the answer sheet like 55 milliliters,
That would be wrong.
Would be wrong.
Yeah. Any more questions? You can also bring Avogadro into this. Okay? How many sucrose molecules, this is sucrose, that's table sugar, are present if we have a 2 molar solution and we have 300 mils of it? Well, the way to do this is to figure out the number of moles of sucrose that you have. Then we remember, Avogadro told us 6.02 times 10 to the 23rd things in a mole. So we know moles, we know his number, we can calculate sucrose molecules. 2 steps, but not hard. Molarity, moles divided by volume. Once again, concentration times volume is moles. Concentration times volume, multiply them together, 0.375 moles of sucrose. Now that we know how many moles we have, and we know how many molecules per mole, we can simply cancel moles, multiply this by 6 times 10 to the 23rd, and we get 2.26 times 10 to the 23rd sucrose molecules. One more variant on all this. This allows us to use mole fractions, mole ratios, I'm sorry. We have potassium sulfate at 2.5 moles. We have 150 mils of it. How many moles of potassium ions do we have? And how many moles of sulfate ions do we have? Well, once again, we need to calculate moles. We have 150 mils, we have 2.5 molar, we have a concentration and a volume that gives us moles, no problem. Then we look at the mole ratio here. In potassium sulfate, there are 2 potassiums and 1 sulfate. Now remember, this is an ionic compound. So when you take an ionic compound and you put it in a beaker of water, it will dissociate completely. So potassium sulfate goes to 2 moles of potassium, 1 mole of sulfate. Mole ratio, 2 and 1. So, back to our problem. Concentration times volume gives us moles. Multiply that out. Our liters cancel. 0.38 moles of potassium sulfate. So, this is our given, and we have a mole ratio. There is 1 sulfate in every potassium sulfate. Multiply that by our given. Moles of potassium sulfate would cancel. We get 0.38 moles of sulfate. To do potassium, the mole ratio is different. It's 2 potassiums to every 1 potassium sulfate. Again, moles cancel, and we get twice as much potassium ion in solution. Any questions? Well, I promised you 2 tutorials, right? We'll have 3 total. This is the second one. This is molarity 2. Molarity 2 is a word problem, but it's exactly the same as your table, just in words. And you have to do some metric conversion when you do it. Now, we've been doing this, you know, we look at milliliters, convert it in our heads to liters. Look at a liter, convert it to milliliters, whatever. We can do this. What volume of a 0.555 molar solution? This is methanol in water. Molar mass is 32 grams per mole. We want 0.37 moles of solute. So we're looking for moles, aren't we? Over here, we're looking for a volume in milliliters. Remember, this is going to give us liters, so we need to change that to milliliters. Moles divided by volume is molarity. Moles divided by volume is liters. Here we substitute in. We're getting 0.666 liters. Liters to milliliters, simply multiply by 1,000, and we're at 666.
Okay.
Totally accidental. Any questions? Let's do another one. How many milligrams are in 272 liters of a 1.13 molar solution of methanol again? And here's its molar mass. So we're looking for mass here, aren't we? Moles over liters is molarity. To get moles, concentration times volume gives us moles. Here we substitute, we have 0.872 moles. Now we need to convert that to grams, but we can do that because we know the molar mass in grams per mole. This is our given, here's our ratio, simply multiply them out, and we get 27.9 grams. But nothing's in the block yet, is it? Because the problem said milligrams.
2700.
Grams to milligrams, just multiply by 1,000, 27,900. Yeah,
I got, when I multiplied that out, 8.872, I got 27.95.
0.95 what?
27 point, okay, so I did was 0.87236 times 32.04, which gave me 27.95.
Oh.
So wouldn't that be?
Well, then I made a mistake. I'm sorry.
No, I just.
No,
If
You know,
we were to get
sometimes-
that on the.
sometimes I just do this on purpose to make sure you're paying attention.
I'm just. I don't want to like.
That's
put
okay.
Put that in the
You
the
got
answer
me.
sheet on the test and get it wrong.
Nope, you're good. Believe me, on a test, you got that close, I would be so happy. All right, one more. Volume in mils, 1.75 molar calcium nitrate, and we want 0.0879 moles of solute. So, looking for volume again. Volume is going to be moles divided by molarity. We know molarity. We have 0.088 moles. This gives us 0.05 liters. Convert that to mils by multiplying by 1,000. 50 mils. All right, before we do our last section in this chapter, let's do some exam questions. Molarity of a solution, which contains 10 grams of sodium hydroxide, 500 mils of solution is what? Molarity, we remember, is going to be simply number of moles divided by our volume in liters. Remember, you have to convert milliliters to liters. So half a liter. Remember moles. We know a mass. We know a molar mass. There we go. 10 divided by 40 divided by 0.5. 0.05 or 0.5 moles. Mole. Any question? How many grams of calcium nitrate? Here's its molar mass. Do we dissolve in water to make 500 mils of a 1 molar solution? It's a real lab experiment, isn't it? Well, here's our given 0.5 liters. We're looking for a 1 molar solution. That's 1 mole per liter. That's a ratio. Those cancel. 0.5 times 1. We're looking at half a mole. This stuff is 164 grams per mole. 164 grams per mole. Those cancel. Basically half of that going to be, 80 something. 82 it was. Another question. We have a molarity. We have a volume. We're looking for moles. That's so simple. We've done this before, haven't we? Concentration, volume, and we're looking for moles. Here's our basic equation. Again, volume is going to be molarity times moles. Concentration times volume is moles. That's what we're after. So here's our concentration. We're looking for moles. That's our volume. Simple calculation, 1.78 moles. On one version of an old version of exam 2, this was the extra credit question. "200 mils of sodium chloride evaporated down." You get a beaker all covered up with crusty stuff. We weigh it, it gets 1.56 grams of solid sodium chloride. What was the original molarity? Our original molarity, moles of sodium chloride divided by our volume, which was 200 mils, 0.2 liters. We have a mass, we have a molar mass, 1.56 divided by 58 divided by 0.2, 1.33 moles per liter. Any questions? Real exam questions. All right, our final subject in this chapter is dilutions. You have a solution, you know its concentration, and you dilute it.
The tutorial is really tedious because you have to remember four equations.
Well, concentration times volume is moles. That's easy. And you have a 3x5 card. Okay. You can also bring your 3x5 card from exam number 1 if you want, because questions always overlap, just in case. All right, dilution of solutions. There are two ways to do dilutions. One is called a serial dilution. In a serial dilution, you're starting off with a stock solution here. You take a known volume, in this case 10 mils, we add it to another beaker here with 990 mils of water, total of 1 liter. Then, you take 10 mils of this solution, add it to 990, get another liter. Take 10 mils of this solution, add it to this one, and do that again, 4 times. When you're done, you are diluting this by a factor of 100 every time. So if we had a 1 molar solution, this would be 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8 molar. There's no way you could go into the balance room and weigh out a milligram. Doesn't work. This allows you to make very, very, very dilute solutions. If we continue this out, 12 dilutions, 12 serial dilutions, and we started with 1 molar sodium chloride. After 12, we would have 32 sodium ions in solution. 32. Down from 6 times 10 to the 23rd. So this allows you to make solutions with darn near nothing in them. This is why it is used to make homeopathic drugs. They have nothing in them. They're not even regulated by FDA because they have nothing in them. They are diluted down so far, whatever. Ever heard of strychnine? organic molecule. When I was a kid, you could walk into a drugstore, and there on the shelf would be a bottle of strychnine, 49 cents. Okay. You could use it to kill rodents. Little old ladies used it to kill off husbands. Whatever.
Oh, I thought we were talking
Arsenic too. You could buy arsenic as well. They're all right next to each other. Arsenic takes longer. This is really potent. This is really, really potent.
what is
But you can't go into Jewel Osco and buy strychnine anymore, can you? Well, actually, you can. You can.
one?
It's called cold calm. Children's cold calm.
No, that's why.
Children's cold calm. Multi-symptom cold relief.
You're telling me it has that crazy.
Let's look at the ingredients. I have highlighted 3 of them here. These are belladonna alkaloids. Lethal dose of about 0.2 milligrams. This is a 6C, 10 to the minus 14
Oh, it's
milligrams
nothing.
in the pill. This is yellow jasmine. Yellow jasmine is related to strychnine. It's a little brush sort of thing. It has flowers on it, pollen. That's where the yellow jasmine toxin is. If you walk through that little pile of brush in shorts, you can absorb enough through your legs to kill you, at least make you good and sick. About 10 to the minus 12 of whatever starting sample they use. And finally, this is strychnine tree. Lovely name, Nux vomica. Less than 10 to the minus 8 milligrams, but it's still strychnine, isn't it? Yes. Children's cold calm.
You're telling me
If you have children and you get really frustrated,
You're telling me
It's hand poison, literally.
whatever.
it's not even. It's like
10 to the minus 16 milligrams is what you're giving them.
So
All right.
So it's like
The other way to dilute a solution. You have a bottle, you know what's in it, you know its concentration, you add water. You get a different concentration, don't you? That's simple. But the number of moles in your initial solution hasn't changed, has it? It's still the same. You just added more water. But the number of moles is the same. So we know how many moles. Initially, volume times concentration will give our initial number of moles. V2 times C2 would give the final number of moles. But, because they don't change, these two are the same. So we can take these and equate them and make the magic formula V1C1 equals V2C2. This is how you calculate a dilution. A standard dilution, not serial, but a standard. Let's see. Sodium chloride, 0.53 molar. 500 mil aliquot, that's sample of the solution, is diluted to 1750 mils. What's the final concentration of sodium chloride? Well, we're going to work with concentration times volume, remembering that moles does not change. So, V1C1, V2C2. V1, 500 mils, C1, 0.53. Our final volume, 1750. Concentration times volume, concentration times volume. Divide this by volume. 0.5 times 0.53, liters cancel. Divide by 1.75. Our final solution, the concentration is 0.15 molar. That's simple. Yet another formula to write on your card though. V1, C1, V2, C2.
It's different on the tutorial.
What volume in mils of a 2.1 molar solution do you need to make 1600 mils of a 1.1 molar solution? So we want a 1.1 molar, 1600 mils of it. And we're looking for the volume of this solution, that's V1. We're solving here for the initial volume. We know C1, we know C2, and V2. We're solving for this guy. 1.1, 1.6, 2.1, molars cancel. 1.1 times 1.6 divided by 2.1, 0.84 liters, multiplied by 1,000, 840 milliliters. One equation to remember. And the last tutorial, called dilutions. To what final volume, that's V2, should 140 mils of 2.3 molar volume, concentration, final concentration of 0.56 molar. Here's our equation. Don't forget it. We're looking for V2. That's C1 V1 over C2. Plug it all in. We get our answer in liters. Remember? We're looking for a volume in milliliters. So simply multiply this by 1,000. 580.
Question.
Sure.
When I checked the tutorial, the formula was different. So like, I think it was like V2 equals N1 times V1 divided by N2. I think that was the formula in the tutorial that I checked.
Oh, yeah?
So that also works too, right?
Yeah. Obviously it does. I don't remember exactly how I wrote that, to be honest. It's so many years ago.
Okay, that makes sense then.
Makes sense. One more. 440 mils. That's V1. That's C1. Diluted to a final volume of 0.88 liters. We need to make this both the same units, and we're looking for C2. C2 will be C1 V1 over V2. Simply substitute. Do the math. 0.026 mole. Any questions? All right, well, let's see. A couple announcements here. Number one, on Monday, we're doing Chapter 8, so that's a week from now. That is acids and bases. This is your opportunity to use the log and 10 to the x buttons on your new calculators. You don't often get that chance. Please bring the calculator with you so you can play along. These calculations are sometimes not intuitive, and so doing them in class with me will help. On Wednesday, that's this Wednesday, we're doing empirical formula. I put the correct lab up on Blackboard, so if you printed it early like a good person, you have to print it again, nonetheless. Potassium alum can exist in various hydration states. This is what it looks like. This is also what it looks like. Beautiful crystals you can get out of the thing. But again, you can have different amounts of water, of hydration in the crystal. It depends on the conditions that you crystallize it. Water of hydration looks something like this. This is for the one with 12 waters. There's our potassium, there's our aluminum, here's our 2 sulfates, and we have 12 waters around them. Depending upon how many waters, you get a slightly different crystal shape. The way we're going to do this quite simply is to take the stuff, going to weigh out a certain amount, heat it up. When you heat it up, the water goes away. We'll weigh it again afterwards. From that, we can determine the empirical formula of what we started with. Any questions? All right, pay attention on this one too. Today we did 3 more tutorials. Molarity 1, molarity 2, and dilutions. Now, I know that tutorials 1 was taken off after the exam, like I said it would, and that some of you wish that it was back. Well, this is early warning, but after we complete Chapter 9, the following weekend, I call Amnesty Weekend, I will put Quiz 1 and Tutorials 1 back up online for 3 days, Friday, Saturday, and Sunday. You can get in there if you need to, try to get more points, do them all weekend, and you're good. Any questions? All right, again, here's our tutorials. These are in tutorial 2. Good luck. Have a good day.